Today I will discuss first lecture about dynamical mean field theory. I will present some introductions. Of course, many other aspects will be developed in the next lectures. So I will build on what I've presented yesterday on various aspects, especially impurity models. Let me start with a few, to warm up general remarks. What we are interested here is about strongly correlated systems. So what do we mean by that? I mean, by weakly correlated systems, we would mean systems for which, quote unquote, the standard model of metals applies, meaning basically renormalized independent fermions, either through the Fermi liquid theories, which I reminded you yesterday briefly, and density functional theory. There will be a longer introduction to it in the lecture tomorrow by Olivier. These are really the two pillars of electronic structure theory, standard electronic structure theories. They work well for weakly correlated systems, almost by definition, but for strongly correlated systems, they don't. Interaction produces new physical effects, new phases, many instabilities, and qualitatively different effects. So there are many examples of such systems. Of course, very famously, some cuprate superconductors, some routenates. I'm sure Antoine will talk a lot about strontium routenate in his second lecture about DMFT, multi-orbital systems, ion systems, more recently bilayer systems, but also interfaces of oxides, for example, alloys, or ultra-cold systems. So it's really a large variety of systems for which we will want to be able to compute and to which we can apply DMFT. So briefly speaking, if we look at materials, typically the system we're going to be interested in are systems where we both have valence bonds and core electrons being localized around the atoms. Some orbitals are usually partially localized, like the 3D and the 4Fs, because the orbitals, due to the orthogonality properties, are closer to the nuclei. And roughly speaking, basically one can say that the electron hesitates between being delocalized, localized, let's say, at short time on the atom, and delocalized at very long time. So we will have a competition between local excitations, atomic-like excitations, rubber bonds, and long-time Fermi-liquid-like, for example, excitations. So we find that typically in the periodic table with transition metals, rare earth, and actinides. If I want to draw a cartoon of strongly correlated physics compared to free electrons for the spectral function, which is the object I was presenting yesterday. As I showed yesterday, I mean, you have for free electrons a peak that will go across the Fermi surface. For correlated systems, we will see a quasi-particle peak, as we discussed yesterday, but of course also a structure at higher energy. It's called the Hubbard bonds, at an energy of the order of the atomic excitation. And the key question is the competition between these two features, which you can see in other quantity as well. Here's a picture, for example, of optical conductivity in some cuprates, where you can see that as a function of doping, very quickly, spectral weight is transferred from low energy to high energy. So it is this competition which we want to capture, the atomic-like excitation about bonds, the quasi-particle peak, and that's what DMFT has been built to do. I already basically said that too, but I'm reminding you, the Hubbard bonds, meaning the structure of high energy in the spectral function, is a remnant of atomic transitions. If you take just the atoms and you look at the different multiplets of the atom, you can find some structure. Of course, it's renormalized by the rest and by interactions, but that's what it comes to. I've solved yesterday in detail the Hubbard atom, so I'm not going back to it. And so the conclusion here is that to understand, for example, the energetics of the mode transitions we're going to see later on various phenomena, it's important to have an accurate description of the multiplets of the atoms. With all of these U for a simple case, in more complicated multi-orbital cases, the Hund's coupling, GH, and there will be the content of the second lecture. DMFT, because it solves an atom in a bath, will be able to do that. So indeed, what is the main idea? DMFT versus DFT. DMFT is describing the system as an atom in an effective bath of independent electrons, which I will represent with this little cartoon. Here you have an atom with a spin or whatever, and a bath with a function curl G on an impurity problem. The central object which we are going to approximate is a Green function, G of omega, the object which we looked at yesterday. And this is to be contrasted with DFT, where density functional theory, Olivier will talk more about that tomorrow. Just here, I'm just saying that here we would take about independent electron in effective periodic cone-sham potential, and the central object will be the electronic density. And of course, tomorrow the lecture will merge this idea of DFT with what I'm going to present for DMFT. Today, I'm going only to look at models, Hubbard models, just to do the basics. DMFT is part of a larger family, which we now call quantum embeddings. It looks better, I suppose, where we take a material or a model like the Hubbard model, and we extract some local degrees of freedoms to build an auxiliary problem, which we then re-embed into the lattice. We'll come back to this picture when we'll see the equations. And there is a lot of ways of doing that. Which degrees of freedom are you really going to select? What are the correlated orbitals you want to solve, the one you don't want to solve with this method, and how exactly you do these embeddings. The main idea is that it's a good idea when atomic physics plays a major role in the physics. That's just the idea. Now, I need one or two more things I didn't have time to finish yesterday, almost. I just wanted to show one slide I couldn't show yesterday. Quantum impurity model, what we did is, what I did yesterday was to look at the non-interacting problem, and then the Anderson model. So just to remind you, we looked at the Anderson problem here with atom, its interaction U, its bars, which are represented here with psi, and in blue, the red mean is associated to the atomic problem. And there is a typo, that's stupid, but anyway. And the action form, and the typo, it should be D here, and for some reason it has been transformed into a C, because I made a correction, stupid error. So that's what we looked yesterday. We have our Anderson impurity problem. Now, as I draw on the board, we have a spectral function from the D, which is as follows, where we have the Hubbard bonds at an energy of order U over 2, minus U over 2, and we have this quasi-particle peak here of width decay, which can be very narrow when U increases, and as I showed, when U increases, the peak narrows while staying pin here at omega equals 0. That's the particle Hall symmetric case. That's for lower temperature, low temperature lower than Tk. If the temperature goes above that Tk, that peak simply melts, and you have a structure without the red peak. That resonance called the Kondo-Abrikosov-Schul resonance, it is a many-body effect. It's not an obvious effect. And it appears at or close to the Fermi level. The slide I wanted to show yesterday is indeed a calculation of these. That's an old simple calculation you can find in this book by Hewson, which is a good reading if you're interested in impurity problems, even though it's a bit older now. This shows the evolution of the spectral function A of omega as a function of omega for different values of u. This is a simple calculation, fourth order self-energies, but it's enough to illustrate what we mean. At u equals 0, which is this curve here, you see the Lorentzian, as I was plotted yesterday. And then when u increases, you see the fact that the peak narrows here, becomes very narrow, and you build a satellite structure at u equals 4 and u equals 6 here. And you can see it's quite quick. However, everything stays pinned here at omega equals 0. That's this Friedel-Sum rule. So that's just not just a sketch, it's just an actual calculations in the particle symmetric case. So, again, the analogy we have is between the lattice, where we have the spectral function here, as I described before, and this spectral function of the Anderson impurity model. We have the same kind of structure. We have Hubbard bonds in both cases, or atomic excitation in this case, and we have a quasi-particle peak, as we discussed yesterday, and described by its self-energies, and expansion at low energy of the self-energies. So the point is, which we want to do, is that DMFT is going to transform this analogy between the two problems into a formalism. So that's what we want to do now, is to find out and describe the equation. I will do that in details. Yes? There are questions? Yeah. Yes?
Just so I can follow up a little bit. On the left, you said we're solving the lattice problem.
Yeah.
So on the right, we have an Anderson impurity model.
Yeah, it's just a cartoon, of course, yes. Yeah.
So how did we solve the lattice problem on the left?
Yeah, I'm not saying I've solved the lattice problem. I'm making a cartoon of what the lattice problem would be.
We know the lattice problem would have.
Yeah, I'm just anticipating on results, just to motivate the methods. I have not solved everything at this stage. Okay? Exactly. It's just, motivation. More questions about that? It's just, warm up. All right, so now I can start, indeed, looking at the dynamical mean field equations themselves. Okay, so as I said, it's an atom in a self-consistent bath. Reference work by Metzner and Vollard, Antoine Georges and Gabriel Cotillard in the early 90s. So, equations. What we are going to do, and that's probably the central slide of the presentations, so I'm going to spend some time on it. The first things what I want to do is I want to approximate the self-energy on the lattice, which is a function of k of omega, by a local self-energy. Okay? In this way, self-energy, sigma is the spin here. That's the self-energy on the lattice problem. So I take my Hubbard problem, and I want to build an approximation for it. I'm going to say that it is the impurity self-energy, so it's approximated by a local self-energy, which is computed by an impurity problem, an auxiliary quantum impurity problem, with the action which we discussed before, and I'm sorry, the typo is still propagated here. I'll fix it later for the records. And the self-energy is defined by, its natural definition, compared to the bare propagator curl G naught. So I will call curl G naught, like yesterday, the bare propagator here of the impurity problems. G imp is impurity green functions, so it's just the correlation function in terms of the effective action. And the problem is, that's good. Now I need to tell you how am I going to construct the bars of the quantum impurity problem. So the bars is going to be determined by the last equations. We are going to request that the local gain function on the lattice here, G loc, is equal to the impurity gain functions in the bars in question. And the local gain function on the lattice is, of course, the sum over k of the lattice green functions with sigma lattice or sigma impurities, but I already said that they are equal, so I can as well replace it in this equation. So that is a self-consistency condition. It's an implicit condition for the function G0. Okay. A priori, the function G0 can depend on spin. Well, I'm not going to be very interested here in systems in a field. It's possible to do that, but in practice, you can forget the spin index. Everything will be diagonal in spin in this presentation. So again, we make an approximation of our lattice problem by saying its self-energy is given by an auxiliary quantum impurity problem self-energy whose bath has to be computed with a self-consistency condition requesting the equality of the local grain functions between the two systems. Now, that's the approximations. Why? We're going to see some justification for it during the lecture, but that's what we put. There could be different way of doing self-consistency. You could ask, why do we use the same interaction that we use for the Hubbard problems? These sort of questions, but that's the basic equation that we have for the Hubbard model. So here I'd like to pause for a second and ask whether questions are clear or whether there are questions. Yes, please.
Can you clarify, just to make it super obvious for me, the difference between these calorific G's and these normal script G's?
I'm sorry, I didn't understand the question well. Say it again.
Can you
Clarify
clarify
the
difference between the fancy font G and the simpler normal G for the different Green's functions?
So
The two G.
this object
Yeah, the side.
and which one? The difference between this one and which one?
G impurity.
This one.
To the right.
This one.
Has a different script, and I just want to make it very clear if the difference in these scripts imply a difference from the lattice problem versus the impurity
No.
problem or something.
Curl G is exactly what appears in the impurity problem here, that the bare propagator of the impurities. That's the notation for it. Curl G is defined by the action here. We used it for that, and I'm only using it for that. Now, the sigma is the self-energy, G is the grain functions. The distinction between lattices and impurities is lat for lattices and imp for impurities. Loc meaning local grain functions, which means, of course, on a lattice, because it's otherwise sum over k's. Okay. So curl G is just a notation for the bath of the impurities.
Okay, so the path of the impurities is this blue object.
Yes.
Okay.
The bath is the hybridization of that G.
Okay.
Yes.
Does that mean curly G will have the hybridization function G? Does that mean that curly G has the hybridization function?
Yes, like yesterday. So in fact, I have it on the next slide, but yes, is omega plus mu minus delta, like we had yesterday during the impurity problem. Yes.
In which sense this is an approximation? Meaning that in the other model you have, let's say, Dewey organ in space U-term in Hamiltonian. In the impurity model you have that term. Shouldn't be the, let's say, the self-energy the same as the impurity model in the case?
No, because in the lattice, the self-energy will depend on K. It will have a strong K dependence, which we are neglecting here. So that's already a large approximation. And in fact, in some regime, in many regimes, this approximation is not sufficient. We need to go beyond and correct it. So that's the core.
Which regimes?
I will show it in a moment. All right, so, sorry. So I would like to point out one aspect of these equations, which are the fact that they are exact, just to mention the equation, in two limits, which are simple limits, but still. The first one is when u is equal to 0. Because when u is equal to 0, the self-energy is 0, so of course it's k-independent. The approximation works well for free electrons. The second one, which is maybe not as obvious, is it's also correct in the atomic limit. So in the atomic limit, by definition, it means well, we take a Hubbard problems and we neglect the hopping term, meaning we only have independent atoms. Okay? If we have only independent atoms, the self-energy on the lattice is just the self-energy on the atoms, and you can check for yourself, playing a little bit, that indeed putting the hybridization delta equal to 0, meaning G0 equal to the bare part without the hybridization function, will solve the equations. So the equation is also exact for an isolated atoms. So by construction, DMFT interpolates between these two limits, which we said are two extreme cases: weak coupling, where we have weak interactions, and atomic limit, where we have all the atomic physics and the multiplets. Okay. Now, what is the whole of the bars, really, these approximations? The role of the bars in the quantum impurity problem is to create the Kondo peaks, as we have been discussed, therefore the quasi-particle peak. You can contrast that with simpler approximations. After all, I could think about doing an approximation where I approximate the self-energy on the lattice just by the atomic self-energy. That's easy, I can compute the atomic self-energy. It's called the Hubbard-1 approximation. That's fine for an insulator, but in a metal, I would not get the quasi-particle peak. I need the bars to build the quasi-particle peak in the impurity problem, which then will give me a quasi-particle peak in the lattice. So DMFT has both characters, as I said before. So now let's go a little bit more into understanding these equations for the local approximation of the self-energy. So that's the same equation as before. The green function on the lattice is approximated, the self-energy on the lattice is approximated by the impurity self-energy here. So it's, this formula. So what do we have? And that goes back to your question, what exactly does the approximation contain and does not contain? Because our self-energy is a local self-energy, it has an expansion like we described yesterday as a function of frequencies. It contains a quasi-particle residue in a metal. So we can describe a metal. And the first remark is that the green function G lattice still depends on K. The self-energy does not, but the green function does, right? So we can describe a Fermi surface in DMFT in this way, right? The lattice depends on K. However, well, we can also, get the quasi-particle residue Z, the effective mass, the coherence energy scale, finite temperature lifetime, because we can extract them from sigma. Yesterday, I wrote the expansion for sigma on K and omega. You have an approximation of sigma, you have such an expansion, you can extract Z and M star. So we can describe a Fermi liquid. Somehow, the quasi-particle peak on our lattice is parameterized or described by the quasi-particle peak in the Anderson impurity model. But of course, there is some limitations, and it goes back to the previous question. Because the self-energy is independent of K, Z, M star, gamma are all constant along the Fermi surface. They are independent of K. That's the first constraint. Second, they are related. If you go back to the equation I gave you yesterday for the effective mass, you see that there is a dk sigma term, which is of course 0 here. And as a consequence, the quasi-particle residue and the effective mass are related. I mean, Z is equal to 1 over M star. Oh, yes, in yesterday's notation, this is MB, 1 over M star. And that's a constraint which may or may not be good in experiment, corresponding to in real systems. Here I show a little plot of what happens from an angle resolution photoemission spectrum, meaning spectral functions, in a corner of a Brillouin zone for a cuprate, for a superconducting cuprate in normal phase. What you can see is that there is a high, and this is the Fermi surface, so that's two different dopings. Here you have the Fermi surface, so 0, 0 is here, pi, pi is here, let's say here. And you have the Fermi surface along this, which is just a place where the spectral function is very large at finite temperature. And you see that there is a strong anisotropy between the diagonal directions and the off-diagonal directions, called the nodes and the antinodes. And in such systems, clearly DMFT will not be enough. That's a major limitation. That's why we will need to have extensions, like cluster extensions, have been built over the years. So we can do metals, but with some limitations. If these limitations are a problem, you need to extend the method later. Does this answer your questions about limitations? Yeah. Good. So now we have a system of equations. How do we solve it? Okay? It's not totally obvious because if you look at the equations, you have an impurity problem and you have a self-consistency condition. So typically we do it with an iterative technique. We solve the impurity problem, let's say we know an approximation or a starting point for G0. We solve the impurity problem, then we compute the impurity Green function and impurity self-energies. We recompute using these equations. We compute sigma imp, and we use a self-consistency condition to recompute sigma imp, and again this equation to recompute G0. So we use an iterative technique to solve the equations because the equation that is implicit in curl G, so there is no expression that tells you curl G equal in the general case. So there are two parts, of course, in this. The easy part is to solve this, these simple systems. The hard part is to solve the impurity. That's called the impurity solver problem. You have a quantum impurity problem with a bath given to you. Solve it. Compute the Green functions, compute the self-energy numerically with an equation. I will say a few more words about that at the end, if time permits. Otherwise, also Michel will tell you about one class of impurity solvers starting later. Monte Carlo. Yes?
At the first step, you compute both G and impurity and the self-energy impurity. Then in the self-consistency, you use both of them?
Yeah.
What are you solving for?
No, I'm computing self-energy, computing G imp, then self-energy, putting back self-energy here, recomputing G imp, then I get back G, curl G with the equation here. At convergence, I will get back the same curl G I had before. What?
At the first step, are you not computing regular G imp by calculating the correlator, or you're not calculating the correlator?
It's a circular method, so I need to start somewhere, right?
Yeah, okay, let's say you started with some G0.
Okay, I start from some G0. I compute these two things. I compute G, that's the hard part from the impurity solver. Then I compute the self-energy from curl G, right? Because I have this and I have this. And that's it for my impurity solver. Then I put my self-energy into here, compute a new version of G impurity. And then for that new version of the impurity, give me a new curl G, a new approximation of curl G, and then I loop. Of course, when I've converged, I will here get the same curl G I started from. Okay? Is that better? Yes.
Is this
That's okay, go ahead.
Is this self-consistent loop like the mean field self-consistent?
Yes, and I will come back to that in an analogy in a second. It's similar to a Weiss mean field.
In that sense, do we have like low or minimum concerns? Like even if it's converged, but it might be a local minimum, the actual.
Yes. Can we keep the question for later? Because yes, you can have paramagnetic solution, ordered phases. Exactly, it has the same characteristic as mean field. We can answer that later.
To close the self-consistency loop, I have to use the
solution that these inversions may become problems. Is it clear from the onset?
Yeah, you mean?
Kinds of settings this can become difficult? Or
Yeah? Yeah. You're raising a very important question. These are the mathematical equations. In practice, you may want to compute the self-energy with better but equivalent formula that avoid the inversions, for example. There are techniques like that related.
So in practice, I just have to check whether or not numerically.
Yeah, in practice, it's usually fine, but you can. We can rediscuss that. That's a more technical question when you actually do the solving. But has nothing to do with the formalism itself. More questions? Okay.
I have a question.
Yep.
So, this says almost always conversion.
Oh, almost, yeah.
When you say almost, does that almost speak about that sometimes it doesn't converge, or about perhaps multivalentness of the solution?
Sometimes it's harder to converge. Sometimes it's slow to converge, but it's rare. Usually, I can say, that and just we need being careful and writing always in a slide. But
Can you get a problem of multivalentness of the solution?
yes, we will find different solutions and different regimes in one of the solutions afterwards. Again, I'll answer that a bit later. That's a very good question. Okay, can I move? Good. Just a small remark. That's in the effective impurity problem. You can write it as an Hamiltonian form like we wrote yesterday with V lambdas and psi lambdas and all of these. I just want to make clear, because sometimes there are confusions, these parameters which we have nothing to do with the original hoppings and energies in the Hubbard model. They are an effective bars which you do in your approximation. That's just a small remark. Okay, now one thing is, in fact, the DMFT equations depends only on the density of state on the lattice, and the reason is that the k dependence on the equation here is only through epsilon of k. So in practice, it's useful to use sometimes the density of states, d of epsilon, which is the sum of delta minus epsilon k. And if I introduce the notion of a Hilbert transform, which is this expression, the integral of d epsilon over z minus epsilon, then this expression is nothing but the Hilbert transform at that value. Okay. So the only thing that matters for DMFT from the lattice is a density of states as a function of the energy. That's what enters the equations. So because of that, there is a very common cases which you will use all the time, which is a beta lattice. So the beta lattice is a specific lattice which has no loop. It's just a tree. It looks like this. There is no loop. This is a lattice with connectivity z, which is a number of neighbors. Here z equals 3, and hopping between the different neighbors. So that looks like a bit of a strange lattice, but it has a very nice property. When z goes to infinity, that's free electrons on the lattice. The green function of free electrons on the lattice and such lattice have a very simple equation, meaning that their self-energy is equal to T squared G, meaning the green functions itself. As a consequence, you can solve these quadratic equations. We'll show that the density of states on such a lattice is in fact a semicircular density of states, so a function which is like this, which is just a semicircular between minus t and 2t. Okay, so that may look like a curiosity. The fact is, in this lattice, the self-consistency condition of DMFT simplifies drastically. That's why we use it a lot, especially in the exercise, because it's simpler to use. And also, a semicircular density of states is, any good as any other foratory problem. It has no specific singularity, zero frequency. So that's what we use very often. So for the records, I will go quite quickly on the next two slides, but I put them just because sometimes they are useful. How do we simplify the self-consistency condition? And then I will write the final equation on the Bethe lattice. The fact is that these are mathematical properties. The Hilbert transform of such functions can be done explicitly. And the mathematical property that's useful is that, in fact, if I look at this transformation, the Hilbert transform d tilde of zeta, its reciprocal function is very simple. The function that you know, such that r of d is psi, is just a simple function, t squared g plus 1 over g, as you can read from the equation. So the Hilbert transform has a very simple property, and again, if you take this property, you will be able to show that the green function, the curl G function here has a much simpler function, much simpler property that the hybridization function delta is simply t squared times the impurity green function. So you don't have to sum all of the sum over k's that there is before. And the proof is here for the record is that you have these self-consistency conditions, which is the Hilbert transform. You use the R functions, replace it, and you'll find exactly this result. So, same equation, but summarized. The same equation, we have self-consistency, so the impurity problem, and we have a simpler self-consistency condition in the case of the Bethe lattice or the semicircular density of stage, which means simply delta equal t squared g. That's why we use it a lot, and you will use it in the exercise. Of course, as soon as you want to compute transport, things become a bit more complicated because this lattice is a bit bizarre, but we are not going to go there today. It's okay? Yes. Yeah.
Last time we considered a simple bus of 3 electrons.
Yep.
And what will depend on the quality of calculation of the bus complexity? So is it usually okay to consider such simple bus?
The bus is a bus of 3 electrons, so it has a density of states. If your question is whether we can use something flat at the 0 frequencies, or?
Do we really, like, I'm asking if it's important to have some complex bus that represent the actual system, or we can just use the simplest bus of 3 electrons?
Yes, it's important, and we'll see that in the equation, in the solution afterwards. So, now, now DMFT is, so that's one way to view it, which is to view that fact that self-energy is approximated by an auxiliary problem. And, then we can refine the approximation, make it more complex, and more accurate. There is another way to look at DMFT, which is to look at it as a mean field theory, meaning that we are looking at describing the system as an atom in an effective environment, which is the bath, in an analogous way that we solve the Ising problem in a mean field theory. So I would like to put the equation in front of the classical Ising problem, just to go on this analogy, and I think this was one of the questions before. Yes? I understood the question.
For example, using that bad lattice just to obtain the results.
No, I'm just saying, in the case of the Bethe lattice, the self-consistency is simpler, so we use it as a toy problem.
So using lattices code the criteria that we use.
We'll use a similar tool, yes, to solve them. Yeah. It's just a small simplification when you do Yeah, it will not change anything else on the machinery. Okay. So let's go back to standard classical statistical mechanics, a simple Ising model where we have classical spins interacting with snare balls that the Ising model sigma I equal plus or minus 1. And here we have very old mean field theory. We all know. What do? We take an order parameter, which is the magnetization, the average value of the spin, and we will write an effective Hamiltonian, which is this spin in an effective field representing the environment, meaning HF times sigma, and the effective field is given by the magnetization of the near-boring sites times J. So M times J times the Z, which is the number of near-bores in such a system. And we have done that in elementary classes. We know that we can solve this effective problem. It's just a simple Ising speed in a field, so that's very easy, and we get the fact that the magnetization is hyperbolic tangent of beta times the effective field, therefore a self-consistent equation. And we know that we can do a lot of things with mean field, qualitatively correct for some quantities, not for others, like critical exponent, but that's a different story. And it's derived typically in large dimensions, or for example. So I would like to show that analogy between the two equations. Here we are. Why is some of it missing? Okay, there's some. Okay. So we have the Ising problem that I just described. Here we talk about the Hubbard problem. We have our effective action and effective impurity problem, which is, of course, much more sophisticated than the spin in the Ising problem with an effective field, but that's an analogous role. The order parameter will not be just the magnetization, but the thing that will play this role here is a Green function, the local Green function, which we solve from the effective action. And the self-consistency condition, which was easy here, is replaced by the equation which we had written before, which is an implicit equation for the bars. So that's another way of viewing the DMFT equations. You take one atom in the Hubbard problems and have a bar that represents its environment, which is self-consistently determined. Same equations, slightly different point of view. And that gives the name of the method historically. Okay, that one I will skip. Okay. Now, yes. I need to, okay, that's the 2 point of views on DMFT. Now, in order to prepare also for the next lectures, I will need to give a slightly more formal derivation of DMFT, and what I would like to show is that DMFT is in fact an atomic approximation, but not of the self-energy, but of the Luttinger-Ward functional phi of G. And that will be necessary in order to do some generalization later. So the idea here is a very general idea and method in statistical physics. What we do is that we pick up the relevant physical quantity, x, we build a functional, and we find this expression of a functional, a ground potential, and we approximate the complicated part, quote unquote, of the functional. Example, you want to describe a magnetic transition, then you take the magnetization, you take the ground potential associated to the magnetization by doing the Legendre transform on the magnetic field, and you do a mean field approximation. In DFT, you build the functional of the electronic density rho of x, and you make LDA approximations, or another one. Here, we can build DMFT as a functional of the Green function, the local Green function x. So how do we do that? You take the action of the Hubbard model. So that's the action on the lattice of the Hubbard model with a bare propagator G here. and a small additional field which I added here, an interaction. And we look at the free energy as a function of field. As a function of field, so that's the free energy. The green function is clearly the derivative of the free energy with respect to h. H is the source for the green function is this. And you can build a function gamma, which is the Legendre transform, as you do in thermodynamics, to eliminate h for the green function. You obtain a function gamma of g, which is, okay, the Legendre transform, which has exactly this form, trace log g plus this term, plus a difficult part here, which you don't know how to compute exactly, which is the Luttinger-Ward functional phi of g. The function here is critical on the physical solution, meaning d gamma dg is equal to 0, corresponds to the physical solution. So no DMFT here. This is standard, techniques in the many body. You can build these things. So again, gamma is given by this. Phi here is such that if you look at this equation, d gamma dg equal to 0, you'll find the first one, g minus 1, equal to the bare green functions minus sigma g, and sigma is a derivative of phi. So phi is just a functional that's such that if you take the derivative on the physical solution, you'll get the self-energy. So that's a Dyson equation as a functional equation of the green function. This Luttinger-Ward functional has a diagrammatic representations, which is a sum of diagrams which are called two-particle irreducible. Oh, that's absolutely not great. Sorry. What happened? Okay. Which is a sum of diagrams which cannot be cut by cutting two lines, whatever. That's, dramatic. So we know how to enumerate them. We know how to write all of these diagrams for the Luttinger-Ward functional. And it is a building block for what's called conserving approximation in the many-body field, following Boehm and Kadanoff. I will leave the fact and the details that this functional has subtleties, which Michel has found years ago, and not go too much into this. But phi is this function. So what is DMFT? DMFT corresponds exactly, yes?
There was a term, the skeleton diagrams.
Yes. Two particle irreducible diagrams, also called skeleton diagrams. That's the same, it's just a name. Different books, different names. The definition of DMFT is that you take only the local diagram in phi, in real space, same point on the lattice, in terms of diagrams, exactly. So phi here of Gij is some phi, which I call phi 1, which are the diagrams which are local on space. That's another, well, I'm going to say it, but that's another definition of DMFT, and it's a bit strange because it's a definition where there is no bars and no impurity, but it's equivalent, as we can see. And the reason is that you have your, sorry. If you look at the diagrams for phi, phi does not depend on the bare propagator, just on the full propagator on the vertex. And you can see that, in fact, the impurity problem is just an auxiliary problem that will sum exactly the diagrams, which are the local diagrams, in the phi propagator. So you're going to use the impurity problem as an auxiliary machine to solve these approximations. And it works exactly because the full propagator is a local propagator on the lattice, that's the first DMFT self-consistency equations, and because the self-energy, which is d phi over dj, because phi is now local, is a local object which is sigma imp. So it gives you exactly the DMFT self-consistency equations. So these two definitions are strictly equivalent. Again, we can see from there that the method DMFT will be exact in two limits for u equals 0, because phi is equal to 0, so this approximation is correct. In the atomic limit, because, well, exactly phi is the sum of the local diagrams for each atoms. And you can prove using this way that, in fact, the methods will be exact in the large dimension limit. That's how it was originally introduced. Meaning if you take the system in an hypercubic lattice of dimension d and scale it correctly in the large dimension limit, this approximation becomes exact. You can find proof in the standard reviews. I don't want to go into any of this technicality here. It's just a statement. And because it's true in large dimension limit, that's why it's equivalent to a mean field, because that's also one way to derive mean field approximation. Okay, so in short, phi DMFT is an atomic approximation. It means that the two particle irreducible diagrams are the sum of all the atomic diagrams, but it's an atomic approximation on phi, not on the Green function, and on sigma. In a sense, locality is a control parameter. And the consequences are multiple. The fact, first, it's very easy to, first it makes it a diagrammatic method. Okay? It started as an approximation that, you know, we have an impurity problem as a toy, we make an approximation for the self-energy. Here, we have put that as a diagrammatic technique, so it's exactly within the framework of diagrammatic methods. The consequences is that it's easy to mix with other diagrammatic techniques, and that will be the starting point idea to build GW+DMFT techniques. It opens many different ways of generalizations because you can go beyond an atomic approximation for the local diagrams with two atoms, neighboring atoms, clusters, for example. And as a consequence, it is conceptually straightforward to generalize to non-equilibrium. Now, it's hard to solve out of equilibrium, but because we have a diagrammatic techniques, we can transform into Schwinger-Keldysh techniques. There's no, conceptually, it's not difficult. Technically, it's, of course, very hard. Okay? And again, we can continue the analogy with DFT, because in DFT, you have a functional of the electronic density. Here, DMFT is a functional of the Green functions. Well, you can make a functional of both, and then you'll be able to go into the DFT plus DMFT territory. That's the point of view we had in this old review, and you'll hear much more about that tomorrow. Another consequence of that is also if you want to compute thermodynamics or the free energy, you should be careful that the free energy on DMFT on the lattice in the DMFT approximation is not the impurity free energy. And the reason is that the free energy, omega, is related to phi by this equation. That's, you can find that in good old books like Abrikosov-Gorkov. You relate the energies to the potential phi. This is completely general, true for a lattice, for any problem. You have the same equation for the impurity problem. The free energy of the impurity problem is related to phi of the impurity problem times the same thing, except there is no K space. Therefore, because this phi is expressed in terms of the impurity phi, we can eliminate these and relate the free energy on the lattice to the free energy of the impurities plus a correction term here, which corresponds to the difference of these two terms. So yes, you solve your problem with an impurity problem, but the free energy that you have for the impurity problem is not the approximation of the free energy for the lattice. You need to have an additional term. Okay, so is there a question at this stage? Because I have finished everything I wanted to say about the formalism. Now I would like to say a little bit about mode transitions and show you the solution of mode transitions using DMFT, which is a classical example of it. Yes?
About the functional, so we can derive DMFT in terms of functional, but usually for other methods, for example, for diagrammatic extension of DMFT, it can be not the case. So it's also a question like if this functional really exists.
Yes, it depends. For many, it is the case. For many cluster methods, you can derive it with functionals in cluster DMFTs. For methods with vertices, also you can do it with functionals. Yes. So it depends.
And also, if we mix some other methods with DMFT, we need to take into account that their self-energy already contains some part of the
Yes.
correlation, and we need to somehow subtract.
Absolutely. That will be one of the questions for GW+EDMFT. It will be explained at that stage. You can eliminate double counting diagrams. Is that what you mean? Yes. That's the point of having a diagrammatic technique. You'll be able to eliminate double counting diagram, which is much, much harder, impossible to do in DFT plus DMFT. Because it's not diagrammatic.
Is it only within the DMFT approximation that's straightforward to go from the impurity free energy to the lattice free energy? Or if I put extensions on top of DMFT, I'm screwed?
No, it will be generalized for clusters, but you need, of course, to work out the generalization. All right, so good. There have been questions, so a bit. How much time do I have? Okay, so I will do a bit less and that. Okay, so first I'm going. What I want to do now, and I want to explain the basic idea of the mode transitions and how we get the mode transitions from the DMFT equations. That's a standard case because that's one of the things you're going to do in the tutorial. I will skip some of the material because I have a bit too much, but let's start with that. First, we have the Hubbard model. Well, we have already discussed that. I don't need to go much into it. We are going to look at this model, especially at half filling, as a function of U. We could discuss doping another time. And what we are interested in is really to understand what happens at intermediate coupling. So what is a mode insulator? Okay. Let's look at the Hubbard model at half filling. A priori, we can have 1 electron per site in average. At small u, you have a metal. You have a half-filled bond, you'll have a metal. If U is large enough, you will get an insulator because the charge motion is frozen. As you can see in this simple picture, you have 1 electron per site. The spin can fluctuate in various ways, but electrons can't move because if they move, they pay a very high price, U, to be on the same site. So your motion will be frozen. That's a mode insulator. Okay? At half filling. Of course, the spins themselves interact. There will be antiferromagnetic interaction between them. You can have magnetic orders, antiferromagnetic orders, for example. I'm not going to discuss that too much. So that, no. The question is, in this mode insulator, what I would like to understand is how we do the transitions between a Fermi-liquid metal, a Fermi-liquid at low U, when you have small interactions, to this mode insulator, where we go for very large U. So here, let's say 0 doping at half filling along this line. We have a Fermi-liquid, we have a mode insulator. What happened in the middle? What happened if I approach that from a high doping regime, where we have a metal? And how is a metal destroyed when we go to a mode insulator? And a lot of things happen when you do that, because these metals close to mode transitions are very fragile. They lead to a lot of instabilities. They have rich phase diagrams, small coherence energies sometimes. So they are very interesting. So I want to show two of them in materials. One of the things which the systems, we can take some systems where we vary the pressure. Instead of, we can't vary, of course, U in a system, but we can vary the pressure, and the pressure will effectively change the parameter of the effective model that we use to describe it, meaning U and T. One of the systems is V2O3, which has as a function of temperature and pressure different regime with the Mott insulator, the metal, and an antiferromagnet. Or these systems, I hope nobody will ask me the exact name because I don't. They are 2D organics, but have a very good model as a simple about problems. And again, as a function of pressure and temperature, we can see the Mott insulator, the Fermi liquid, and the antiferromagnet. And there is a quite rich phase diagram in these systems, which we like to understand. So that's one of the things we like to understand. Another one would be the high temperature superconductors, which I'm sure you all have seen before as a function of temperature on dopings in this class of oxides. You have a Mott insulator, a doped Mott insulator that gives rise to superconductivity and all sorts of interesting phenomena. So we like to understand Mott physics for that reasons. All right, I don't need that, and I don't need that. So now let's see what is the solution for DMFT for a Hubbard problem, one bond at half filling, exactly the model I was mentioning before. I take the DMFT equation, I solve them using, for example, the Monte Carlo method that Michel will explain in the next lecture. What is the result? All right. So here is the phase diagram. Again, half filling. D is a half bandwidth at the unit of energy which we take here. We look at the phase diagram as a function of temperature and interaction U. We see that we are going to find, from the solution, we are going to find two solutions, a metallic solution and an insulating solution, let's say at low temperature, and a crossover between the two at high temperature, a coexistence between these two phases, and an hysteresis, so it's a first-order phase transitions that will end at a critical point at a temperature Tc. That's very similar to a liquid-gas transition. Okay? Except here, this is the Mott insulator and the metal. Now, as a function of UC, there are two critical, as a function of U, there are two critical value UCs where two things appears. The metal gets destroyed here when UC at UC2, when the quasi-particle residue goes to zero. If your quasi-particle goes to zero, your metal disappears. And in reverse, the insulator, if you decrease U and follow this solution, the insulator will get destroyed at UC1, where the Mott gap will close, and these two values are different, meaning, again, that you have a coexistent regimes. So let's look a little bit more at the solution of this phase diagram by looking at the spectral function, so the local spectral function, Gm, Glog, the same, in the two phases. So again, first the metal. In the metal, that's the spectral function. So that's solved with IPT. I guess that's exactly the one that you will be doing in the tutorial. Solver, right? Yeah. And the spectral function as a function of U will start with something that has no structure. Then you start to see the formation of the quasi-particle peak that narrows and opens in a gap here for intermediate value of U. And when U becomes large enough, the peak is simply gone. You are in the metallic phase. But here in this region, in the insulating phase, here in these regions, you are in the metal. You can do the analysis the same as we did yesterday for the self-energy. And you can plot the self-energies, and you will find something very similar to what I plotted yesterday, with the slope due to the quasi-particle peak, the omega square due to the imaginary part of the self-energy. Okay? So that's a metallic solution. Now, if you go from the insulating solution, you will get, well, a gap, which is a mode gap of order U. You can, again, plot the self-energies, but in this case, as I mentioned yesterday in the Hubbard atom, the self-energy will diverge at low frequencies because of the special symmetry. So that's the solution. I didn't tell you how you solve the equations. This is done with a very simple solver. You will do that as an exercise. What I want to discuss is, again, these set of solutions. So what we see here is exactly what I mentioned in the introductions. We see that when the interaction increases, the spectral weight is transferred from low energy to high energies, and we find, the structure at low energies are on the gap. Meaning you can capture simultaneously the Fermi liquid with a low coherence scale, because the coherence scale is given directly by the quasi-particle residue here, and the bar bands. And DMFT does not describe only the Fermi liquid, but both. It describes the finite temperature effect and the function as a function of U. Therefore, that's why it's a dynamical mean field, because in order to capture this phenomenon, you need to describe the dependency as a function of frequencies, as we can see in this graph, and therefore, that's why you need to have a self-consistency on an object that depends on frequency entirely, not just on the quasi-particles properties, for example. And that answers your question you had before. In order to solve the problems of the impurity problem, think about the beta lattice. This is also delta, the hybridization, because delta is G, and therefore when you are here, your bath has a lot of structure, and therefore you need to solve with methods that are capable of solving complicated structures, because that's a self-consistent equation. Right? And by the way, that's why we needed to develop all sorts of new techniques to solve DMFT. Impurity problem is a very old topic. There is a lot of techniques that people have used to solve analytics, integration, whatever, and this problem in Anderson problem, but they all use a flat bath with a very high energy scale, and they are not applicable in DMFT for precisely this reason here. That's why we need to have specific techniques. So we can illustrate, for example, the low coherence temperature on thermodynamic quantities. Here's the specific heat that you have here. Here you find the Fermi liquid behavior, the linear as a function of temperature, the Fermi liquid behavior, and then some intermediate regimes. And here the gapped behavior for large U, that's of course in the metal, that's in the insulator. This one, the dashed one, is in the insulator. Same thing for the entropy. You can find that the entropy will be quenched at very low temperature from log 2, which is fluctuating spins, which will be a trivial description of the description in the DMFT of the insulator, which we see. So here we have an illustration of a very low Fermi liquid coherence scale, which the method can capture. It can compute below it and above it. Now, to be complete, the phase diagram which I shown, that's better color, but not just that. What I did here is to solve the equations, and that goes back to another question of yours. Sorry. Yes.
I have a quick question. You just showed this phase diagram a couple slides ago.
Yeah.
And you mentioned in this DMFT we had a coexistence of solutions.
Yep.
Does that imply DMFT is best suited for first-order phase transitions?
Best suited, I wouldn't say so, but it can handle them.
Can you also describe second-order phase transitions using
You can describe the vicinity of the critical points, for example, which is second-order phase transition. Okay. Yeah. So it's not specifically suited for that, but it can do that. And that answered one of the questions. Is there are two solutions? Here you have two solutions. Right? And the point is that if you look at low temperature here, you also have, in fact, an ordered phase. The equation I wrote are in paramagnetic phase. And that's going back, I think it was your question, that if you have a mean field, so exactly like other mean field, you can solve the paramagnetic solution down to the order inside the ordered phase, and you of course have the ordered solution and the non-ordered solutions. So in most of the presentations, DMFT is solved in the paramagnetic phase, but in fact, there is an ordered phase in there. And if you do not do anything, in fact, the ordered phase will be very high and completely remove the critical point. What we want to solve is a system which is frustrated in order to remove the antiferromagnet to a lower temperature. So point number one, we can solve DMFT in an ordered phase. Okay? It's a mean field. We can convert it in an ordered phase. For example, in an antiferromagnet, by using two sublattices. Okay? Maybe we can do that in an exercise. I don't remember. But we can certainly do that. So we can solve this phase. A small remark on the frustrated systems. If you take, for example, the beta lattice, you can see that you have the same equations for frustrated systems if you put first neighbor hopping and second neighbor hopping. That's the equations are almost the same, T1 and T2 here, compared to T, than the paramagnetic equation that you had before. So when you solve the paramagnetic equation, what you're actually doing, because you only depend on the density of states in your self-consistency condition, you're solving, in fact, the frustrated system in practice for the physics. So with that in mind, the real phase diagram which you will find is this. So this hysteresis I described before, and this, and different regimes here above the critical point to be described if time permits. Okay, so DMFT in that sense is a high temperature method. It starts from high temperature, like mean field. It's good and better at high temperature. When you go to lower and lower temperature, your system will develop more and more instabilities, more longer range interaction, which cannot be captured in the local self-energies, and there will require more and more corrections. So the more you go into complicated regimes or lower temperature, the more you expect to have corrections. So there are this is a method that fundamentally starts from high temperature and decrease. To be contrasted with other approaches to the many-body problem, like exact diagonalization, obviously, or tensor network techniques that start from understanding the ground states and up as a function of temperature. So these two methods work in different directions. Okay, so how much time do I have? Do I have the time to show a few experiments? I can show a few things with experiments. So I like to show this comparison with this organic compound, which has been done almost 20 years ago, but it's a very nice experiment. Organics have interesting properties, in particular that you can put a lot of pressure on them. And you can see here the pressure is in a couple of 100 bars, which is quite low, so they are very soft materials. So we can span the entire phase diagram, well, experimentalists can the entire phase diagram without changing the chemical composition and all of that, so it makes it simpler. So that's the experimental phase diagram, which I mentioned before. We see in experiment that there is, in fact, a Mott insulator regime. We see that there is a Fermi liquid regime, and an hysteresis, a first-order transition, a critical point, some other regime here, and a little bit of antiferromagnet. So it looks a lot like the phase diagram, indeed that's the same graph, that's the same diagram that we have before, except that it's flipped, right? It's because this is plotted as a function of the pressure, which is more or less 1 over u, so it decreases when u increases, and this is plotted as a function of u. So diagram, the experiments and the theories are flipped with respect to each other. So experimentally, people can see, for example, the hysteresis. What they measure here precisely is the resistivity. Yeah? So that's not exactly a one-body quantity, but you can recover it from it. I'm not going into this. You can see, for example, the hysteresis as a function of P in the different phase. So you can go see one phase, and then when you go down in the conductivity, you will see the other phase. So you can see the hysteresis region here, and that's how it's mapped carefully by looking at the behavior of the conductivities between these two regimes here and there. And in the metallic regime, yes, sorry. Yeah. There. Yes. So in the metallic regime, you can extract the behavior of the resistivity as a function of temperature, getting the standard T square for a metal, and this coefficient A, which is as a function of pressure, and see indeed that you have so different metals, and see the disappearance of the metals when you approach here in these regions by looking at different slices as a function of temperature. Yes?
Well, we have on this phase diagram, we have sometimes positive slope and sometimes negative slope. Isn't that a bit like
Yes. It's not. I mean, the theory is not that precise, right?
No, in the sense of it's not conventional, right? Usually, first order phase diagram is constant.
Yeah. That's how the experiments comes out. But yes.
But it should be like the same slope. It's just the error was clear.
That I don't know. I will need to check the paper again. I don't want to say, but yeah. Okay. So that's So that's the example I wanted to show. That we can go into many details on the experiments, but in the interest of time, I just would like to focus really only on this one here, the fact that we get these similar phase diagrams here. One region which I am interested here and to show here is the bad metal regimes. What happens here? What happens here is the fact that the quasi-particle peak which we had in DMFT is in fact melting because of temperature. So, like in the Kondo problem, when you increase above TK, then your quasi-particle peak melts. As a result, your resistivity will start to degrade, and you're losing the metal. It's called the bad metal regime. So we can also map the higher temperature regime. But I would like to save a couple of minutes to say one or two things about the impurity problem. So I will skip the part of this about the solving the impurity problem, because otherwise it won't be good. So that we already seen. We have an iterative method. We need to have an impurity solvers. Impurity solvers are and still are in DMFT largely the bottleneck. So to be precise, for one bond system, it's fine. We can solve it. We have methods to do it. As soon as we want to do more complicated atoms, multi-bonder problems, clusters of a certain size, it's still largely a bottleneck today. So as soon as we want to have a more complex atom than the Hubbard problem, with more degrees of freedoms, spin index or spin orbit problems, and then some of our methods, fails or become very slow. So the point is, so the quantum impurity solver is still a major challenge in the field. Just to give a few words, why? Because we always want to do larger and larger systems. We want to compute them faster. We want higher precision. We would like to compute in real time. And really the point that I like to make is that you are going to see some simple solver in the tutorials. You're going to hear about Monte Carlo in great detail in the next lectures. There are other techniques, and fundamentally, algorithm development is crucial here, and help is very welcome if you're interested in this kind of topics. The toolbox that we have these days, Monte Carlo, Michel will lecture about that. Exact diagonalization, where you represent the bars with only a few sides and do a long shows techniques. Works well, but of course very limited in size. Monte Carlo works very well, but it's only in imaginary time. It can have sign problems. It has stochastic noise, so it has limitations. Numerical renormalization group is a very old techniques used to solve impurity problem. It has made a lot of progress recently. But it's still limited, let's say, about 3 orbitals or 4 orbitals for some systems. Tensor networks are very promising, but still have their own limitations. In addition to that, there is a large list of approximated solvers. You will see one later in the exercise, which is iterated perturbation theory, which is just taking the first diagram of the self-energy at the lowest order, and many other approximated solvers like the NCA families, or even more basic ones. That I've already explained before. That I will show you later. And conclusion, this is just the beginning, because I have shown you only the basic equations for a simple about problem with one bond in paramagnetic solutions. There are many different directions in which you want to generalize that. You may want to, and I put a few of them here, you may want to, of course, go to more realism. That's what we're going to do. One of the questions there is, how do you choose the correlated orbitals? Let's say you have a problem with copper on oxides. You may want to do a DMFT on the copper, but not on the oxides. So how do you write? You need to have a self-consistency condition with every atoms, but solve only some of them. So that's one of the questions which will be discussed. You may want to remove some of the limitation we discussed about clusters by taking on instead of one site, a couple of sites to have short-range antiferromagnetic correlations, for example. Or you may want to parameterize the K dependence of the self-energy, not being constant as a function of K, but in patches in the Brémond zone progressively. That's this kind of picture here. That's another technique that parameterize the K dependence of the self-energy, so help going beyond the limitation which we have seen. You can do vertex methods. You can self-consist on other things than the self-energy, like two-body green functions. That's a more advanced topic. We can also, because it's a real space method, use it for non-translation invariant systems. You can have, if you have an interface, for example, you can have different impurities at different level, one per a different position in the interface, and solve them together. You can solve disordered systems like alloy. So DMFT is a very versatile technique. It's just a way of approximating self-energies in correlated systems, which assembles. And indeed, the TRIX libraries has been designed to handle that, to build small components like impurity solvers, pieces to hide self-consistency conditions, in order to solve not only the first cases presented today, but all of these different generalizations, and like a small Lego that you can assemble. And so you will see some of it in the next lectures. And I'll leave you with some references, which I'll leave. A very classical review by Georges Kotler, Kraut, and Rosenberg. A more recent one about DFT, DMFT. Some review about the Monte Carlo impurity solvers. And on impurity model, I added a reference. It's a small article of review, which was reprinted in memory of Jacques Friedel, who, by the way, was working nearby at Orsay. On impurity problem, it's a small introduction containing a bit more than the material I presented yesterday, and a small introduction to DMFT as well. It's been published a couple of years ago. And on that, I will thank you and take more questions.